So in our last video on binomial distribution, we learned how to do the calculator steps. But now let's take a look at how we can extract some information such as the expected value and the variance from a binomial distribution. So let's go ahead and dive right in. When you're doing the expectation of a binomial distribution, your mean or expected value is simply kind of like very similar to our last time. It's the number of trials that you're doing times the probability of it, that you're taking into consideration. And then your variance, which again is a different type of measurement for dispersion, which is the square of the variance, which is the square of the standard deviation, is going to be NP times 1 minus P. Okay. Luckily in this class, we don't have to prove that. We just have to sort of take it at its face value. So let's say, for instance, that I am flipping a coin 100 times. Okay. So if I'm flipping a coin 100 times, I would write X is, so I have 100 trials, and my probability of getting, let's say, heads is 1/2. So what is my expected value for all the heads? Well, I'm running this game 100 times, flipping the coin 100 times. I'm going to multiply by the probability, so I would expect 50 heads, which makes sense because I should have 50 heads, 50 tails. Again, I should. So what does that mean for the variance? Well, again, I could just plug it into this formula right here to get that piece of information. So the number of trials is 100. The probability is 1/2. And then 1 minus the probability, in this case, it happens to be the same, also 1/2. So what that means is that the variance is equal to 50 times 1/2. So the variance is equal to 25. And then again, standard deviation, which in our textbook is denoted by sigma, is going to be the root of 25, which means that our standard deviation is just 5. Okay, so that's how you can go about using these equations. So let's take a look at an example problem here. So let's say that X is a random variable such that X has a binomial distribution with N and P. So it's given that the expected value is 3.6 and that the probability of success is 0.4. So let's find N and the standard deviation of X. So let's remember that the expected value is N times P. So if I have 3.6, which is my expected value, I can multiply that by N times P, which is 0.4. Okay, then I can just divide each side by 0.4 and get my number of trials just from this. So if N is equal to 3.6 all over 0.4, that is going to give me a value of N of 9. So if I wanted to write that more formally, I could write that as 9 and 0.4, use my binomial distribution formatting there. Now, what is the variance? Well, I'm given that the variance formula of X is NP 1 minus P, which is right down here, NP 1 minus P. So N is 9, P is 0.4, and then 1 minus 0.4 is just 0.6. And I can put that into my calculator, and I will find that my variance is equal to 2.16. And again, my standard deviation is equal to the root of my variance, so 2.16. So my standard deviation is going to be equal to about, I should use my squiggly, about 1.47. Okay, so that's another way that you can use this if perhaps the information is, one side of the equal sign or the other. So now let's take a look at a different type of example problem. So this one is interesting because it's quite a mouthful to read, but it's actually not too bad. So we basically have two machines that are making light bulbs whose quality is being inspected. So managers have found that the probability that the first machine's defective light bulb rate is 0.3, and the probability that the second machine produces a defective bulb is 0.2. So now inspectors take a sample of 6 bulbs from the first machine and 5 from the second, and they use these two different binomial distributions to model the number of defective light bulbs in the samples from the first and second machines respectively. So let's go ahead and compare and contrast the central tendency and spread of these binomially distributed random variables. So what that means is let's take a look at the expected values. So how many values should I expect to be, or how many light bulbs should I expect to be broken from, well, the first machine? So I know that my number of bulbs I'm taking is 6, and I have a value of 0.3. So my expected number of light bulbs broken is going to be 1.8. And then my expected of Y would be 5 times 0.2, again, just NP, as we discussed above, and that is going to give me a value of 1. So what I can say here is that X has a higher expected value. It has a higher number of expected light bulbs to be broken, on average, of course, and I would say it's about twice as much. So on average, machine X or the first machine is going to have twice as many broken bulbs as the second machine. So that's one way to interpret that. And now we're asked for this another spread of central tendency. Let's go ahead and look at the variance of x, which again is n p times 1 minus p. So the variance of x is going to be equal to 1.26. And then my variance of y is going to be equal to n p 1 minus p. So my variance of y is equal to 0.8. So what I can say here with the different variances is that the first machine has a much wider spread in the predicted or the expected number of bulbs broken than the first machine. So there's more variation, there's more variability, there's a little bit more spread. So I hope that helped you see how we can use our expected value formula as well as our variance and standard deviations to apply to our binomial distributions. It's kind of the same thing that we've done before, just now in a new context. And I hope that helped, and I'll see you all in the next video.